In this video, let us discuss about regularization techniques in deep learning. So first of all, we should understand what is regularization, right? So that's really important to know. So let us try to understand that regularization is any modification we make to a learning algorithm that is intended to reduce its generalization error, but not its training error. Try to understand the concept, what it is trying to say. Regularization is any modification we make to a learning algorithm that is intended to reduce its generalization error, but not its training error. So how do I understand this better, right? Because if we are going to study about regularization, we have studied in machine learning that, so we try to improve the performance of the model with some regularization technique, right? So most of the times, the problem that we face in data science is basically about overfitting, right? So like we have come across such situations, which means that the model performs well on the training data, but it was not able to predict test data, right? So we have seen this, right? So what are we trying to understand in this session is what is regularization and what are the techniques to use in regularization, right? So just look at this picture. This will tell you a lot about it. So here you can see that the first one, it is basically the underfitting model. Why do I call it as underfitting model? Because you can see that this is how the points, the data points are distributed, and this is what my model says. So in this case, what I can expect is with the training also, it will perform badly, and also with the testing it performed badly, right? So this is what the underfitting means. Now look at this one. So my model is so flexible, it is trying to learn a lot about it. So in this case, our training accuracy would be high because my model is so flexible and it is learning about the data points well. But what could be the problem over here? So the problem is about the testing data. So how will be the performance in the test data? That's going to be really low. So now look at this one. This is perfect. Why do I say it perfect? So I can tell you that in training also the performance is good and the testing performance is also good. See, one point you have to always remember, say my model is giving 95% accuracy with the training data and say 79% accuracy with the testing data. I do not really want that. But if my model is giving 79% accuracy with the training data and 79% accuracy with the testing data, I'm okay with that, right? So here what we can expect around 50% with the training data and 50% with the testing data. In both the cases, it is performing very badly. Clear, right? So this is what we can understand about basically the underfitting model, overfitting model, and the generalized model, right? So this is what's happening over here. So what is happening as we move from the first image to the last image, we can see that our model is trying to learn so well and the noise from the training data, but it will perform very badly in the unseen data, right? Fine, so this is clear. Otherwise, I can say that the complexity of the model increases such that the training error reduces, but the testing error doesn't. So now let us look into the next picture. Here you can see about the training as well as test over here. So In x-axis, model complexity is taken, and in y-axis, error is being considered, right? So here what you can see, this is basically about the training data set, and this is about the test set, right? So with respect to the model complexity, how the error is changing, right? So this is what we are trying to understand over here. So now, let us try to understand, recollect the concept of regularization. Regularization is a technique which makes slight modifications to the learning algorithm such that the model generalizes better. So what are we trying to achieve? We are trying to achieve this one. So basically what will happen over here? It will improve the model's performance on the unseen data as well. This is what our requirement is, right? So now let us try to understand how regularization helps reduce overfitting, right? So already I have told you what is overfitting, right? So here we have seen, right? On the training data, my model is learning a lot about the training data, but it will try to struggle when I test with the test data, right? So here you can see that here I have shown the picture of neural network, right? So here what is happening? Overfitting, because you can see two types of data over here. I mean the data points or the labels over here. One is X and a circle, right? So here what is happening over here? The model is so flexible and see perfectly it is doing, right? Perfectly it is doing the task, right? So in machine learning, we had a good idea that regularization penalizes the coefficients. So here in deep learning, it actually penalizes the weight matrices of the nodes, right? So let me show you the next picture. Here you can see that what is happening now. This sounds to be an underfitting model. So just think that our regularization coefficient is so high so that some of the weight matrices are nearly equal to 0, right? So in that case, what will happen? We will get a simpler linear network and it will underfit the training data. So such a large value of the regularization coefficient is not that useful. So what we have to do? We have to optimize the regularization coefficient in order to obtain a well-fitted model. So we are trying to get a good regularization coefficient. We need to optimize the value of regularization coefficient to get a well-fitted model as I shown over here, right? So this is clear. So what kind of regularization techniques are there in deep learning, right? So now we understood how regularization helps in reducing overfitting. Now we will try to learn the most important techniques that we use in deep learning. So the first one is L2 and L1 regularization, data augmentation, early stopping, and dropout. So what is meant by this L2 and L1 regularization? So this is basically the most common type, right? So this is actually the most common type of regularization, right? So actually we have studied in ML also. So what will happen over here? These will update the cost function, right? This will update the cost function by adding another term known as regularization term, right? So what is this cost function? Cost function is equal to loss within bracket and writing C, a binary cross entropy, So it could be anything, okay? It is not necessary that it should be binary cross entropy. So just I'm writing an example over here, plus regularization term. So when I add this regularization term, the values of the weight matrices decrease because it assumes that the neural network with the smaller weight matrices leads to simpler models. So it will reduce overfitting to quite an extent, right? So here the regularization term differs in L1 and L2, right? So in L2, so let me write the cost function now, right? So cost function is equal to loss plus lambda by 2m into, right? So here, what is meant by lambda? Lambda is regularization parameter, right? So this is basically the hyperparameter which can be optimized to get good result. So L2 regularization can also be called as weight decay. Why we call it as weight decay? Because it forces the weight to decay towards zero, but not exactly zero, right? So actually in this, we penalize the absolute values of the weights, right? So unlike L2, the weights may be reduced to zero here. So it is very useful when we are trying to compress our model. Otherwise, we usually prefer L2 over it, right? So here we have seen, okay, so let me tell you about L1 also. Then we will have a comparison. Okay, so this is about L2 and let me write about L1. In L1, how does the cost function change? This will be equal to loss plus lambda by 2m into summation, right? So let me repeat the point over here. In L2, lambda is the regularization parameter. It is optimized for better result, and this is called as weight decay because it forces the weights to decay towards zero. But here in L1, what is the cost function? Loss plus lambda by 2m into summation this, right? So here we penalize the absolute value of the weight, right? So it is not like L2. The weights may be reduced to zero, right? So it is very useful when we are trying to compress our model. So otherwise, we usually prefer L2 over it, right? So hope this is clear to you, right? So how do we write code for this L2 and L1 regularization? So basically from Keras import regularizers, right? And then in the model, we will be adding like a kernel regularizer. There, if you want to add L2, you can write dot L2 and you can specify the learning rate over there, right? So the next one is about data augmentation. So let us discuss about data augmentation. This is the simplest way to reduce overfitting because the simplest way to reduce overfitting is to increase the size of the training data, right? So in machine learning, we are not able to increase the size of the training data because the labeled data was too costly, right? So what we will be dealing with the images, whenever we deal with the images, what we do is we increase the size of the training data. So let me clear this first. So here, what do we do? We try to increase the size of the training data, right? So it could be rotating the images or flipping the images, scaling the images, shifting the images, right? So this is what we will be doing, right? So this technique is actually called as data augmentation. So here, this provides a big leap in improving the accuracy of the model, right? So here, how do we write the code? From keras.preprocessing dot image import image data generator. Why I am saying this? Because if I'm handling with the images, this is what I do. And then I'll be writing like whether I have to go ahead with the horizontal flip or whatever technique I want to do, that I can add it in the image data generator, right? So this is about data augmentation. So the next one is about early stopping. This is also a kind of cross-validation strategy. Here, what we do is we keep one part of the training set as the validation set. Okay. So when we say cross-validation, so one part we keep it for the validation set. So what we do over here, when we see the performance on the validation set is getting worse, we immediately stop the training on the model, right? So this is basically called as early stopping. So let me show you the image so that right? So you can look at this image. So here you can see that we will be, stop the training at this dotted line, because after that our model will start overfitting, right? So clear, right? So here for this early stopping, the code is from keras.callbacks import early stopping, and then early stopping we may write monitor equal to val underscore err, and then patience also you can denote. So what this monitor denotes is that is the quantity that needs to be monitored. So here basically it is about the validation error. Patience means it denotes about the number of epochs with no further improvement, after which the training will be stopped, right? So I hope this is clear, right? And the next one is about dropout, right? So what is this dropout? Let me tell you that how this will work. This is actually very interesting technique that we use in regularization. It gives us a very good result, and the most frequently used regularization technique. So how it will do is, like, at every iteration, it will randomly select some nodes and removes them along with incoming and outgoing generation. So actually what will happen over here is, like, in each case, so let me show you the dropout and explain, so that so you can see that in each iteration you can have a different set of nodes, and this results in different outputs. So this we can call it as, like, something similar to ensemble technique in machine learning, right? So ensemble models usually perform better than a single model because it captures more randomness. So similarly, dropout also performs better than a normal neural network model. So here the probability for choosing how many nodes should be dropped in the hyperparameter is the hyperparameter of the dropout function, right? So here the probability of choosing how many nodes should be dropped is basically the hyperparameter, right? So due to these things, actually dropout is usually preferred when we have large neural network structure in order to introduce more randomness. So hope that is clear, right? So let us try to understand. Let us try to understand this in detail. Okay. So let me show you the picture and explain to you. So the first one, as I told you, L1 and L2 generalization. Here, basically, the formula is basically the cost function is equal to loss plus regularization term, right? Loss plus regularization term. So these are the most common methods that we use. Actually, here what happens is, these will update the general cost function by adding another regularization term. So when this term is added, the values of weight matrices decrease, because it assumes that a neural network with a smaller weight matrices leads to simpler model. So it will avoid overfitting. So in L1 regularization, we can consider the absolute values of weights. In L2 regularization, here you can see that sum of squares of feature weights, right? So here it will take the weights to be small, but does not make them zero, right? Does not make them zero. In L1, it will make it to 0, but here in L2, it does not make them 0, and it does non-sparse solution, right? The next one is about data augmentation. Actually, this is being used in computer vision widely because we try to improve the size of the data. So the testing accuracy should not be affected by changing position of the object or its size, right? So here, basically, we try to do some transformations of the images. So if there are large number of training patterns available, then we can go ahead with some neural network model that can learn the invariance approximately. But here it includes with the training data set a large number of examples of the effects of various transformations. So for translation invariance in an image, the training set should include examples of object at different positions. That is what you can see over here, right? So you can see different positions. This is basically called as data augmentation. So it helps to increase the training data set. So there are also a few ways of increasing the size of the training data. So we can also do flipping or scaling. In flipping itself, we can do horizontal flipping or vertical flipping. We can do shifting. All these kind of techniques we can do, right? So the next one is about early stopping. So on testing the data set, if the loss begins to increase and accuracy begins to decrease, then the model starts to perform, right? So at this level, the model have the low variance and it can generalize the data well. So training the model further would increase the variance and lead to overfitting. In that case, particularly, we try to stop it earlier. That is why it is called as early stopping, right? So when we test it, if the loss begins to increase and accuracy decrease, the model stops to perform. So we may get low variance. So that's the reason we go ahead with the early stopping, right? And the next one is about the dropout. So here, this already I have explained about it. This is the most common and most used technique in the deep learning because of the good performance, and also it reduces overfitting. So here you can see that some nodes are being removed, right? So at each iteration, the different sets of nodes gets removed and we get different outputs so that the model stops from overlearning. This is actually preferred when we have large neural network in order to introduce more randomness, and it is also helpful to stop overfitting, right? So in this video, we had a very good discussion regarding regularization in deep learning. Hope it is very clear to you. Thank you.